30-minute timer.
Okay, 30 minutes and counting.
All right, let's practice coding and talking. So, first, let's start a new one. I'm gonna get real set up real quick. I just want to make sure that everything's connected. Sure is. Okay, now let's understand the problem here. So, write a program that will calculate the number of trailing zeros in a factorial of a given number. Ooh, this is going to definitely have a performance effect. 1000 factorial has 2568 digits. So the function is going to be called zeros. Let's understand. Wow, you're not meant to calculate the factorial. Okay. We need a program that will calculate the number of trailing zeros in a factorial. We are not calculating the actual value, we are calculating the zeros. So, let's just make sure we got the interface set up. It's going to be a function called zeros. Zero. I feel like that should have an E. And we're just going to return just to make sure we got something here. Alright, so at least one of them's working. Now, how do we calculate this? This is supposed to be a coding exercise, not a factorial exercise. Let's look at the resources to see if it gives us a hint. Well. Yeah, this is not going to help me. There we go. Okay, let's look at a small example. So, what does a trailing zero mean? A trailing zero means that it is a multiple of 10. Okay. So, hey, now that my whiteboard's here, I guess we could use that. So, if it's a trailing zero, that means it's a multiple of 10. Two trailing zeros, obviously it's multiple of 10, it's also a multiple of 100, and this would be a multiple of 1,000. So the number of trailing zeros means that it is a multiple of, or it's tied to this. So here, let's rewrite this another way. If I have, good Lord, that sounds like it's about to explode. Anyway, so if we have let's see, zeros. 1 0 means it's a multiple of 10. 2 multiple of 100. 3 multiple of 1,000. 4 10,000, etc. So, how do we know if something is? We can go through and look at the number and say, like, is it? We don't want the actual result, right? We need to say, is this a multiple of 10, 100, 1,000? Find the highest here, and then boom, that is the number of zeros it has. So let's just look at an example here. Do 3 factorial, so that's going to be 3 times 2 times 1, which is 6 times 1, which is 6. If we do 5 factorial, it's 5 times 4 times 3 times 2 times 1. Definitely seeing some recursion in here, so keep that in mind. But anyway, this is going to be 20 times 3 factorial, which we already know is 6, so 20 times 6 equals 120. So, we need to figure out sort of like the magnitude here. At what point does this become, I'm trying to think like if we can find some sort of a threshold for the input, if we can figure out that at this value it becomes a multiple of 10, or this value becomes a multiple of 100. So obviously this one is a multiple of 10. This one is not. Let's just hone in on this a little bit. What if we do 4 factorial? Well, that's going to be 4 times 3 factorial. So that's 4 times, we already know 3 factorial equals 6. So 4 times 6 is 24. Now that is not a multiple of 10. So, this makes sense. So 5 is a factor of 10, right? So maybe that's how we got into this. What are the factors of 10? We got 1, 10, 2, 5. Okay. So it took till here to become a multiple. So anything times 5, no, an even times 5 is going to be a multiple of 10. Let's see. Let's just kind of, let's graph this out a little bit so we can see what's happening. So 1 factorial equals 1, 2 factorial equals 2, well, equals 2 times 1 factorial, which equals 2. 3 factorial equals 3 times 2 factorial, which equals 6. 4 equals 4 times 3, which equals 24. 5 equals 5 times 4, which equals 120. 6 equals 720. Let's go ahead. 7 equals 7 times 6 factorial. Uh-oh, we're getting big. Which equals, so now this is going to stay a multiple of 10, right? Because we've already passed this threshold, so no matter what we do, it's always going to be a multiple of 10. I mean, stalling to do the math. 14, 49, 50, is that right? Let's do this real quick. 7, 49, 114, 20, yep. So from here on, we're always going to have multiple of 10. At what point do we hit a multiple of 100? Well, let's just spot check some stuff. I don't want to do the actual calculations. So 8 is going to be 8 times 7 bang, which is going to be 0, 32, 3, 0, 4, right? 9 is going to be 0, 18, 27, 28, 2, 6. Okay, not quite there yet. Let's try 10. Okay, 10 is going to take us to the next level. Because now we're going to have this, and we're just going to shift it. 3, 6, 2, 8, 0, 0. Boom. We hit our first multiple of 100. So at what point now see, I'm thinking we can use this information here to figure this out. So our multiples of 100, or factors of 100, obviously 1 and 100, 2 and 50, 3 and 4 and 25, 5 and 20. So see if there's, I'm looking for a relationship between the threshold here at which, you know, the values become multiples of, you know, here. What's the relationship between this threshold or this range between 5 and 10 and this one here? 10 is like another threshold. I could just brute force, I guess, and go through all of these, but I have a feeling it's going to be a pain in the ass. Now, if I multiply let's just look at this last part here. So if I multiply anything times these zeros, it's not going to change the results unless it's, let's see. I don't care about these other significant digits here. I just want to look at, so I have 800, right? No matter, what do I multiply this to get, or what will affect the number of zeros here? Not much. So times 1, it's going to be 800. 2, it's going to be 1600. 3, 24. I mean, we could just go through this whole thing. 5. So let's see. 1, 2, 3, 4, 5. We get extra zeros. And then the 6. Oh, we lost one of them, right? Huh. 6, 7, 8, 9, 10. So 5,600, 6,400, 7,200, and 80,000. Wait, sorry, 8,000. So now we've got extra. So again, at 5 and at 10, we're changing. So what does that mean? As we keep going through this, I suspect that at 15, we're going to get an extra 0. And then 16, we're going to lose that 0. And then when we get up to 20, well, how is that going to change anything? That's just... Okay, damn, I gotta pee. Sorry, this is cheating. I gotta go pee real quick. 1 sec. Alright, I tried to hurry, but I did think about it a little bit. So, broke this down. Our input, let's see. When we look at our input, if it's any we can look at the magnitude of the input, and that will give us an idea about how many spots it moves over in the tens area, right? So based on our input, we can say how many multiples of 10 can go in here, or what magnitude is it, and that sort of gives us the first set of any multiple of 10 is easy. We just count the zeros there and add them on. So like, if our input's going to be like 100, then we know we're at least going to have 2 zeros. So what it really comes down to is figuring out how many zeros come in the single digits, right? So what can give us 10? 1 times 10, but we're not talking about 10. We're talking about single digits, right? So 0 to 9. What can give us 10? 2 and 5. And let's see, or sorry, not 10, but a multiple of 10. 2 and 5 can give us 10, obviously. 3, nothing. 4 and 5 can give us 20. Well, that's pretty much the same as that, though, isn't it? 4, 5, 6, and 5 can give us 30. 6, I think another 6. Going 1 through 9, 6 times 5, 6, 7, 8, 9, 10. 7 and 10 give us a multiple of 10. It gives us 40. 8 and 4 gives us 40. 5, 9. I think these are all the single digits that give us a multiple of 10. So, what if we can use this to say, are we working with one of these single digits? If so, this gives us sort of like the base, 0 count, and then the magnitude gives us sort of the, other zeros. So, for example, what was our input? We looked at, oh shit, I have to restart my timer. Our example we looked at was 5 was the first one, right? So maybe if we could just look at these numbers. So when our input is 5, how many do we get for like magnitude? Nothing. Okay, but is it 2, 4, 6, 8, or 5? Yes. Okay. So yes, it's one of these. So it will give us, how does this work? Because like if it's 5 and 7, that's not going to do anything. Let's just go with this. I'm going to say if it is one of these numbers, then we're going to get an extra. No, that's not going to work. If it is one of these numbers, if it's a 5 or a 4, no, that's not going to work. If it's a 5 or a 4, then it's going to give us, we can't get one extra, because what if a 4, oh, God, I forgot what this was. 120? Let's do it again. 1 is 1, 2 is 2, 3 is 6, 4 is 24, 5 is 120. Okay. So if this is a 5, yes. If this is an 8, what the hell is 8? Does 8 mean anything to us? What's... Well, let's go through this again. This is 720. So yes, this gets 1. And it's a 6. Okay, maybe 7 is going to be, what do you say, 40, 50, 90? 7, 14, 50. This also gets 1, but it's not one of these magic numbers. Shit, man, I don't know. 8, we know it's going to have 1 because it's not going to change this. 2, 3, 0, 4. 9 is going to be, it's going to get 1 also. 18, 27, 28, 2. No. 10 is just going to be 3, 6, 2, 8, 8, 0, 0. Just to extend this a little bit, because I don't understand the pattern yet. Like, past here we get 1. Here we've got 2. If we do 11, it's going to be, what? 3, 6, 2, 8, 8, 0, 0. 8, 8, 2, 6, 3, 0, 0. 8, 16, 10, 11, 8, 9, 9, 3. Now I'm starting to worry my math is getting off, but so this is still 2. I don't know, man. I don't know. Maybe looking at some of the... Hey, you're not meant to calculate the factorial. Find a number way to find the number of zeros. I'm guessing that at 15, it's going to jump to 3 zeros. So my assumption is that every 5, it's going to jump up another number of zeros, right? Okay, here. So here's my guess. So here, 0, here is 1, here is 2, and if 15 would have 3, then the number of zeros is going to equal, what's this, n divided by 5 floored, right? So here it's going to be, I don't know. Let's just give it a shot. What the hell? I have no idea if this is right. Let's try it though. Hey, it passed a couple. So the N30 expected 7, and it got 6. I don't know, man. I need to... I honestly don't know. Let's see.
It's 9 hours.
Oh no. Well, let's find out. Blah, 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 blah. Wait, okay, so it says, I think we're on the right path. So take the number, divide by 5 and truncate, which is 4. And then kind of recursively divide. Oh. Okay, so we need to also calculate. We can't just do 5. We need to kind of walk up and until our division result is a number less than 1. Okay, so we have 923 factors. Okay. Okay. Well, here we go. Let's do this then. So, our example is going to say so we're going to start with our number, and 5 is sort of our base, right? So we're going to keep getting the number of factors until we get a fraction. So let's just kind of explore the range real quick. So we'll start with the constant for the, we'll start with the exponent. Well, let's just call it exponent. And we'll loop through and say while okay, so I just want to see that I can loop through this and look at my result. While my result is greater than 1, do it again and increment. So let's do a classic for loop. For we use that exponent while result is greater than 1. It's not the result, it's the factors. And then we're going to increase our exponent. Let's see, so let's just bail out of here real quick. Make sure our loop is working. So so I'm just bailing out of the loop, great. So result of this equals, let's figure out what size we're working with. So our base number is going to be magic 5 and the exponent. And, well, let's call this our base. Or, even better, the divisor. The result is going to be our n divided by the divisor, as we can see up here. And then so the way it's saying it, that here we get 932 factors. So we will say, instead of having this conditional, we could just bail out of here. So this is our result, and so we're going to add the complete add any whole values here. So we're going to floor the results, and now here we're going to add a condition to see if we should bail or if we should keep going. So let's say if the result is less than 1, break. So we could just change this to, well, let's keep it like that. Okay, that's cool. So this code is ugly. Let's clean it up a little bit. We start with the base exponent. We could go ahead and start there instead. Factors, we're going to keep incrementing. Our condition is actually, we're taking care of that down here and breaking out. So this is cryptic. We could just say true, which just means we're going to keep going. So you might wonder, why did we use a for loop then if we're just going to keep going? Maybe a while loop would be a little bit cleaner. But yeah, we got test that's passing. Oh crap! Well, that's time. Let's go ahead and that's it. Holy crap, man! Not great. I guess that shows it's don't get distracted reinventing the wheel. All right, well, that's it. Ciao. Oh my God, I said ciao.